Here's a problem very similar to questions 7 and 8 in assignment 8B. If we can do this one, you can certainly do number 6, which is easier. And so let's step through it and answer all the questions. We start with the circuit not connected and the capacitor uncharged. And then we'll lift the switch. So this is a piece of metal that we can click back and forth. So I just copied the same design that was used in the problem. So if I lift this switch, it'll connect those two wires. And this will be the circuit. And this piece will be dangling, not connected. So nothing will happen here. And this we could call the charging cycle because the capacitor's going to charge. And then that's question 7. And then question 8 is we'll take the switch from here and lower it, which will make this the circuit. And this resistor will be involved. And the battery then will be dangling, disconnected from the circuit, and won't have any influence on the second part, the quote-unquote discharging cycle. So if you haven't watched the first introductory video, you should watch that first. It's only about 8 minutes long. And so I'm going to assume you've watched that. So we have a charging cycle and a discharging cycle. And in the charging cycle, elements of the circuit may discharge. So we have two basic behaviors for charging and discharging. And those equations are on your equation sheet. So we should write down the relevant equations, what we need to use to solve this problem. So you might do that. See if you can do that from memory, or look up the equations on the equation sheet and see what equations we're going to need to use to do calculations in this problem. Okay, here are the relevant equations. I think I got all of them. So the relationship between the definition of capacitance is also the relationship between capacitance charge and voltage. And so when we're trying to figure out, how much charge is going to go onto this capacitor, or what will its charge be at a certain voltage, we'll need this equation. We need to know what the current in the circuit is going to be at various times, so we need to know this equation. So Ohm's law, the basic definition of capacitance, we do need that. But these are the equations, the two equations that tell us the behavior, the time-related behavior of the circuit. And on your equation sheet, it's written as I equals I max times this 1 minus e to the minus t over RC, where the RC is called the time constant. So this equation could be written with a t and a tau, or a t and an RC. Either way, you should understand it. But what you need to know is, okay, and so this is the charging cycle, because this factor, when it's 0, is 1, and as time goes on, it becomes e to the negative large number, and it goes to 0. So since this factor goes to 0, if you subtract it from 1, that's the charging cycle. So you really should understand the mathematics. And when that factor, that exponential decay factor, appears this way, then you know that the current is going to start high and decay to 0. So the decaying behavior is this equation, and the charging behavior is this equation. And you should know that just by looking at them, not really have to memorize it. And what we mean by the time constant is when the time, as we start the clock, when the time reaches this value, then t over RC will be 1. And when the time reaches twice this value, then t over RC will be 2. And so that period of time, whatever it is, 4 seconds, 4 milliseconds, 4 microseconds, whatever that time is, will be what we call the time constant. And so you should know that the time constant is the length of time that a charging cycle will take to get about 63% charged, and the time it takes for a discharging cycle to get about 63% discharged, or remaining only about 37% of the remaining charge or current or voltage, whatever it is. So, and where did these numbers come from? This number is e to the minus 1. So when the time constant reaches, when the clock time reaches whatever the time constant is, that's a constant value depending on the resistance and the capacitance, there'll be this much of the current left, or this much of the voltage left, or this much of the charge left, whatever it is that we're calculating. And during the charging cycle, after one time constant of time has gone by, the current or the voltage or the charge as it's charging will have reached about 63% of its final charge. And that behavior continues throughout. So during the next time constant, whatever's remaining, it will go 63%. And then whatever's remaining left will go 63%. And so the behavior that ends up being that during the first time constant it's about 63%, then something like 86%, and then 95%. And so what's unique about these circuits is they never actually reach the value, so you can't say, oh, how long does it take to get fully charged or discharged? The answer would be infinity. So we describe their speed of charging or discharging by this idea of the time constant. And I'm not going to write 1,000 equations on the equation sheet, so you have to know that if you're charging, whether it's current, voltage, or charge, this is the equation you use. So this could be V equals V max, or Q equals Q max, or discharging, Q equals Q max, like that. And so, okay, so let's dive into the problem and do it. But that's important. The more you understand the behavior of these circuits, the easier it becomes and the less you have to guess at what you're supposed to do. So the first set of 6 questions comes when the switch is closed in the up position and the clock is started. So at that instant it closes, t equals 0, at that very instant, what are these 6 values? So see if you can do it for this circuit and then come back and check. So here are the values, and more importantly, here are the reasons. So start with the capacitor. What controls the circuit is the capacitor. Capacitor takes time to charge, it takes time to discharge. That's the whole time-related concept, and that's why the time concept is controlled by both the capacitor and the resistor. So you should understand that, right? A bigger capacitor will take longer to charge. More resistance reduces the current, means it's longer to charge. So the capacitor, since it was 0 in the beginning, it has to start at 0. So that's the first thing you write down. The capacitor voltage is 0, and well, really, the charge on the capacitor is 0, which forces the capacitor voltage to be 0, because the voltage across the capacitor depends on the charge, just like the voltage across the resistor depends on the current. That's an important concept. It's the charge that will determine the voltage of the capacitor, not the other way around. And the current will determine the voltage of the resistor and not the other way around. So obviously R2 is dangling. That's going to have 0. That's going to be 0. This will remain 0 throughout this process until we change the position of the switch. So the capacitor starts at 0. That means it's going to charge. That means it's going to follow the charging equation. And since this is 0 and the battery is 16 volts, by Kirchhoff's voltage rule, the voltage across the resistor has to be 16 volts. And since there's 16 volts across the resistor, that means there'll be 16 divided by 25 ohms, 0.64 amps, or 640 milliamps. Sometimes I don't like to use decimals, so I'll change to the next smallest unit of amps. So either way, this is the current, and as the capacitor charges, the voltage and the current through the resistor, and the voltage across the resistor is going to decay. So that's going to follow the decaying equation, what? According to the time constant. So the time constant, of course, will be, let's calculate it. Okay, the time constant ends up being 1,000 milliseconds, 25 times 40, or 1 second. That was purely accidental. So that means after 1 second it's going to be 63% charged. Now we move to the part of the question where it asks us after a time. So let me set that up. So the next set of questions is, what is the conditions in the circuit? What are all those quantities after some randomly picked time? And I thought about choosing 0.8 seconds or 1.2 seconds. And what I'm going to think about right away is, how does that compare to the time constant of 1,000 or 1 second? So this would be less than the time constant, so I would have some sense of what the value should be. This is more than the time constant, so I have some sense of what the value would be based on these numbers of e to the minus 1 or 1 minus e to the minus 1. So let's pick the 1.2 seconds. That's a little bit longer than a time constant. And so the charging should be a little bit bigger than this, and the discharge should be a little bit smaller than that. So go ahead and see if you can calculate those 6 quantities at this time. See if you can do that on your own. All right, I'm not going to make a table of values here, but you should know that the voltage and the current through R2 are going to be 0. And the voltage across the resistor started at 16 and it's decaying, and so it's e to the minus 1.2, that's the time at which we want to know the value, divided by RC, the time constant, which is 1 second. So the seconds cancel. This is a dimensionless number. So it's e to the minus 1.2 times 16 gives us 4.819 volts, or 4.82 volts, rounded correctly to 3 significant figures. And that makes sense because it means out of the 16 volts, it's decayed a little bit more than the 63% or 37% remaining. So that seems right. And in the charging cycle, it's going to be about 70%, more than 63% charged. And so it's at 11.18 volts, or rounded to 11.2 volts out of the 16 volts by doing e to the minus 1.2 subtracted from 1. And as it should be, and a good way to check it is if you take the 11.2 and you add 4.8, you get 16 volts, which is what you should get according to Kirchhoff's voltage law. The sum of the voltages have to be 0. So the sum of the resistor and capacitor voltage at any instant in time have to sum to a negative. These are magnitudes, really. They're negative 16 volts. And then once we have the voltage, we can get the charge. So the charge on the capacitor at any instant will be the capacitance times the voltage at that instant. And so if we take the 11.18, the longer number, multiply it by the 40 millifarad farads, we get this, which rounds to 447 millicoulombs, or 0.447 coulombs. And the current we get using Ohm's law, so we take the voltage across the resistor at that instant, divide by the resistance, and we get the current at that instance, 0.193 amps, or 193 milliamps, compared to the 640 milliamps that we started with. So given that it's more than one time constant, all those numbers seem reasonable. And the last 6 questions are, after a long time, what will these 6 values be? And what is a long time? Is 10 seconds a long time? 30 seconds? A minute? So 10 seconds would be 10 time constant. That's going to be pretty close to the final value. But remember, it never gets there. But certainly after 30 time constants, I think even after 10, we can calculate and see. To 3 significant figures, will it be the final value? So anyway, write down the final values, and then we'll come back and check that. Okay, obviously these remain 0. They're not even part of the circuit. The resistor's decaying. The capacitor charges to 16 volts. Once it's fully charged, there can be no current because the capacitor's at 16 volts, and there'll be no voltage because there's no current. And also, since this is 16 volts and you add this, it has to be 16 volts. So by Kirchhoff's voltage rule, this has to be 0 when this is 16, all of that. And the charge on the capacitor, when it's fully charged to 16 volts, you need to calculate. So 16 times the 40 millifarads gives you 640 millicoulombs using this equation. Okay, this has ended up being a much longer video than I thought. We're halfway done, but I think we've covered a lot of ground. This would be very useful in doing the assignment and on the exam. So one more thing I'm going to toss in that's not on this question. How would you calculate the time it takes to reach a certain amount of charge? So the time constant is, what, 63% charged or 37% discharged. What might also be interesting is, how long does it take to get 50% charged or 50% discharged? So that's going to be a little bit shorter than one time constant. So let's calculate it. It should be less than 1 second. And that number actually is used in a lot of physical situations, such as like the half-life of radioactive materials, which behave according to this same set of exponential equations. These are very common equations in math, science, and engineering. So let's calculate the half time of charging. See if you can do that on your own. Oops, one thing I forgot. We were discussing what does a long time mean. So let's take, the time constant is 10 seconds. 1 second, let's take 10 seconds. After 10 time constants, where are we? And it's very easy to calculate. You just calculate E. The time is going to be 10 times. It's going to be 10 over 1, or e to the minus 10, and this is the number you get. 4 zeros, 4.5 to the e to the minus times 10 to the minus fifth. And if you subtract 1 from that, so you see you're 99.995% charged. So to 4 or 5 significant figures, it's completely charged. So certainly to 3 significant figures, 10 time constants is plenty of time to be completely charged or discharged. Okay, do the 50% charge to discharge question now. Okay, I'll do it for the resistor. So the voltage across the resistor equals Vmax, and it's decaying according to this. And so we want to know the time, because we know this is going to be 50% that. That's what we want to get. And so we divide both sides by Vmax, and we're left with e to the minus t over tau. And the VR over the Vmax is 0.5 because that's our question. When will this value be half its final value? And so we take the log of both sides, and we're left with minus t over tau, log of 0.5, and then we finish the algebra and we get t equals negative tau ln 0.5. There is a decimal point there. And what we get is 0.693. The time constant was 1, so it's 0.693 seconds. So yes, a little bit less than a full time constant. You're either 50% charged or discharged. And knowing how to do this, it would be very easy to ask the question, oh, what would it be if it were 95% charged? So we could just take 95% charge would be where there's 0.05, where the voltage would be only 0.05, the maximum voltage in the case of the discharging, right? So if we take the log, whoops, let me stop. Take the log of 0.05, 95% discharge would be 5% remaining. And if we take the log of 0.5, we get negative, because the negative sign, right, 2.99. So basically 3 time constants it takes to get 95% discharged or 95% charged. Okay, let's go back and finish the second part of the problem. Okay, trying to finish up, we're going to take the switch and go from this position, closed, and flip it down. And so at that instant that it closes, the very instant it closes before any significant time passes, what are these 6 quantities? So try to do that on your own and then come back and check what I put down. Okay, very important. Start with the capacitor. Remember, that's the thing that can't change. So when the switch was up, it was fully charged at 16 volts. And so when the switch goes down, that will change, but it can't change instantaneously. That's the key issue. So that's where you start. 16 volts on the capacitor and fully charged, and that's going to decay. So given this, given the 16 volts, it means that we have to have 16 volts spread out over these 2 resistors. And because there are 2 resistors, they're not going to both have 16 volts, right? Kirchhoff's voltage law. And so how do you find how the voltage divides? You have to find the current. So we know how to do that. We have 16 volts, and that voltage is across 2 resistors. And the 2 resistors are in series, so that's 100 ohms of resistance. That means that there's 100.160 amps or 160 milliamps in the circuit. That makes sense, right? The original circuit had 640 milliamps, and now we have 4 times more resistance. So we have 1/4 the current. And now we can use the current to find the voltage across these 2 resistors, recognizing that because they're in series, both resistors have to have the same current of 160 milliamps or 0.160 amps. So the voltage should be easy. Go ahead and find that. Quite simple. The 0.16 times 25 gives us 4 volts, and 3 times the resistance times the same current gives us 12 volts, and there's our 16 volts. Of course, one of them has to be negative, so the sums to 0. So now, in this situation, nothing is charging. Everything is discharging. And so you can calculate the next set of questions. Let me put that out. Okay, the calculation part. So after 2 seconds, what are all these values going to be? So this, you have to use the equations, right? And we already told you it's decaying. So go ahead and see if you can do that. Okay, so we know these are all decaying. So whether it's VC or IR or VR, whatever it is, it has this form. And so the important factor is this e to the minus t over RC. And so we're asked to find out at 2 seconds. So I put the 2 here, but you got to be careful. The time constant is different, right? Because now we have 25 plus 75 ohms of resistance. That's 100 ohms times the 4 millifarads is 4,000 milliseconds, and 4,000 milliseconds is 4 seconds. So it's e to the minus 0.5. When you go e to the minus 0.5, you get this. Let me just check that. Yeah, that looks correct. And so this is our factor by which we multiply everything. So the 16 ohms will have dropped by this factor. So I get 9.7 volts across the capacitor, and I can use that to calculate how much charge is there now. So it's gone from the, I erased it for something, down to 388 millicoulombs of charge, using the Q equals VC, right? Or C times V. And then we can get the current was 0.16, and so the current is going to also decay, and so you take the 0.16 milliamps, or the 160 milliamps that we started with, and multiply by this, and I got 97 milliamps, or 0.970 amps. And then the same factor times the 12 volts gives me this, and that factor times the 4 volts gives me this. So I'm just using this equation again and again on all these different quantities, and you can see if I add these together, I get 9.71. So there's a little bit of a rounding error there. In other words, these two voltages have to equal this, because the sum of the voltages in this circuit now have to be 0. Okay, so how does it end up? Actually, let's just skip that and end this very long video. It all ends at 0, right? The voltages will all be 0, and the currents and the charge on the capacitor will all be 0. It will all discharge. Okay, we're finally done. I hope this is helpful.